This slidecast covers abstract classes, an assignment, and casting in a hierarchy. An abstract class is different from an actual class or concrete class in two ways. So an abstract class cannot be instantiated, and an abstract class declares at least one abstract member function, which must be defined in all of its derived classes. Now, an abstract function is a virtual function that's declared for which there's no body, no definition provided. Now, remember, virtual functions from our last slidecast are these functions with the keyword virtual. We presented them as a way to have polymorphism so that pointer and reference variables could dynamically, the objects they refer would dynamically determine at runtime which overridden method would actually be executed. Okay, so that's where virtual functions are, and we'll consider a function abstract if we don't provide any, if we don't actually implement the method for a particular class. Now, we use an abstract class in a class hierarchy when we want a base class for two or more actual classes that share some attributes. So we may want to declare some of the attributes and define some of the functions that are common to these base classes. So it lets us do that once rather than having duplicate information. And the items in the abstract class, we want this in cases where we actually don't want instances of the abstract class. We're really interested in these two or more actual classes, but we want to have a single definition of data fields and methods. Now, if we also want to require that the actual derived classes implement certain functions, we can declare them as abstract functions in an abstract class, and this forces every derived class to have to implement it. So if we have an abstract function, then it means the class, the base class, is abstract as well. So the food guide pyramid is an example. It has a recommendation of what we ought to eat each day. Here are the 6 categories of foods in this food pyramid. Suppose we want to model this food pyramid and make each of the actual derived classes of an abstract class called food. And here's our food class in the header file. So we have a class food. It has a private variable calories, and it has some public methods. Now, these 3 virtual functions impose the requirement that all derived classes from food must implement these 3 functions, and we might expect every derived class would have its own definition for each kind of food, because each kind of food is going to have a different percent. So these 3 functions, when they're declared virtual and it says equals 0 in the header file, and there is no implementation of that, corresponding implementation for the food class, then that makes these abstract functions, and food is an abstract class. And then here's some getter and setters for this private variable, and their implementation is here. But if we have just one virtual or one abstract function, then we'll have an abstract class. Here is the syntax for abstract functions, and it's this virtual keyword followed by the function declaration and equals 0. And here's an example from the food class. So a function declared by function declaration, it's an abstract function. So that expression equals 0 is given in place of the function body, and so it must be specified in the class declaration. And sometimes the term is used, a pure virtual function is a synonym to abstract function. So because this class food is abstract, then we can't create type food objects. So this statement would be invalid. We can't have a variable my snack of type food, because we cannot have an instance of of type food because it has some functions that don't have definitions. Now we can use this food type for a pointer variable to point to an actual object that belongs to some class that's derived from food. So here's a statement that creates a vegetable object. Okay, so vegetable it's a derived class from food. So here's the new operator. Remember, it returns an instance of class vegetable, and we assign it to a variable that's it's a reference variable that points to instances of type food, and this is allowed, so we can assign a vegetable instance to that variable MySnack. And MySnack declared this way means it's flexible, that we could assign MySnack to point to any instance of any derived class from food, including vegetable. So here's a summary of the properties of abstract classes and actual classes. The significant rows are those that have no in them. So instances of this type can be created. We can create actual classes. We can't create instances of abstract classes. We can have instance variables and functions defined in both. We can define constants. We can extend the number of these classes, can extend any number. They can also extend another class. Now here, this can declare abstract member functions. An actual class, no. If we've got an abstract member function, by definition, we have an abstract class. We can have pointers to this type can be declared, and references to this type can be declared. Both kinds. So the key differences are here in these rows with no. Now C++ is known as a strongly typed language. Each operand has a type, and the operations can be performed only on operands of the same or compatible types. And this includes the assignment operation. So when we have an assignment statement, we refer to the left-hand side as the L value and the right-hand side as an R value. Now for built-in types, the R value must be the same type as the L value, or there has to be a conversion defined to convert the R value into a value that's the same type as the L value. Okay, that's for built-in types. Now for class types, the assignment operator may be overridden and overloaded. Okay, we'll talk about that in the next section. Now there's an exception to this rule for pointer types. So a pointer variable, an L value, that is of the type pointer to base class, it may point to a derived object, the R value. And we've already seen examples of this. So this is a legal statement. We can have a the left-hand side, we have a variable that's a pointer to a computer class. Computer's the base class. And on the right-hand side, we can have a derived class. So here's a new operator. We create an instance of a derived class, and we can have a computer can point to it or refer to it. But this is incompatible. We can't create a computer, an instance of computer, and then have a variable of type laptop start point to it. Because laptop is a more specific, it's a derived class, and it would refer to an instance that doesn't have all of the information. It doesn't have some of the data fields or the member functions that the laptop instances have. Now C++ has a mechanism called dynamic casting that lets us process the object referenced by a computer through a pointer variable of its actual type instead of through a type pointer to computer. So here's an expression. Now here's this keyword dynamic cast. We have laptop star in angle brackets and then a computer. So it casts the type of the object pointed to by a computer. So a computer is a variable of type computer, and it casts it to type laptop. And this cast will succeed if the object that's referenced by a computer is in fact a laptop object. Now if it's not, then the result is a null pointer. So this casting gives us a type laptop pointer to the object that can be processed just like any other laptop pointer. So here's an expression. We do a dynamic cast of this object pointed to by a computer. Remember, the computer class doesn't have a method getWeight. But if we do dynamic cast so that we create a pointer to a laptop object, then we can reference the member function getWeight. So it will compile because getWeight is applied to a type laptop reference. Here's another assignment statement where we do a dynamic cast of a computer to cast it to a laptop, a pointer to a laptop instance, and now we can assign it to a pointer variable that's a pointer to a laptop. It's valid because this laptop pointer is being assigned to, a laptop, which is the right type. So this casting operation doesn't change the object pointed to by this variable, but it creates a type pointer to it. And this is called an anonymous or unnamed pointer. So using this type laptop pointer, we can invoke any member function of class laptop and process the object just like any other laptop object. This cast operation is called a downcast because we're casting from a higher type in the inheritance hierarchy, a computer, to a lower type laptop. So we're going to use this dynamic cast to always cast down in the hierarchy to get a pointer to a more specific type. And we do that because we're usually starting out with a pointer to an instance, and the type of that pointer is higher up in the hierarchy. So it's a more generic kind of type, and if we want to access some specific information in that instance that's defined lower in the hierarchy, then we need to do this downcast so that we get a pointer of the appropriate type. So Microsoft compilers require you to set a compiler switch to do this dynamic casting. Here's the syntax for a dynamic cast and an example of it. And a pointer of type class name is created to the object referred to by object name, provided that object name is an actual object of type class name or a derived class of class name. So if the object name is not type class name, then the result is a null pointer. So here's a case study for displaying the addresses for different countries that can illustrate why we might like to use this downcast dynamic cast operation. So if we've got different countries have different conventions for addressing mail, and if we want to have a program to display the address in sort of the correct format depending on the destination, now specifically we want to distinguish addresses in Germany and in the United States and Canada. Now in Germany, the building number follows the street name in line 1 below, and the postal code equivalent to the US zip is placed before the municipality name. So here's a typical German address, while the typical US and Canadian addresses are going to read like this. However, the Canadian postal code is in a very different format. So several components make up an address, and there are lots of variations between countries. So one approach would just be ignore these variations, and we merely record complete address lines as strings. But this approach wouldn't let us sort of analyze or validate portions of an address as easily as if we could break them up into their components. So we're going to, by parsing the addresses into their components, we can validate it against a database provided by the National Postal Authorities, and we can generate address labels that conform to the Postal Authority standards. And there are several commercial packages that do this apparently. So the number of components in an address and their names vary from among countries, but we're going to simplify this situation just for our purposes here, and we'll say an address consists of the following data elements. And a German address is organized as follows, and the US-Canadian addresses are organized this way. So they have, they have similar elements, but the ordering and the layout of these elements differ. So because we're originating the mail from the US, the German address will have the additional requirement that the name of the destination country, Germany, be placed on the third line below the line containing the postal code and municipality. So to design a solution, we're going to create an abstract class address that will contain the data elements, because these data elements are common across all different kinds of addresses. This class will also have an abstract function toString, which will organize the elements into the format required for the destination country. And the derived classes, German address, US address, will then implement this toString function. So the next slide has a UML diagram, and the number next to the attribute means it has protected visibility. So here's our UML diagram for our class hierarchy. We have address, which is an abstract class because this toString method is not implemented for that class. It's just declared, as a pure virtual function. And then here are the common data fields. We'll make them protected in this case so they can be directly accessed by these derived classes. And so our two derived classes will inherit all of these data fields, and then it will implement the toString method. So here's our address.h header file. It has a constructor defined, and here is the pure virtual function toString. Here are the protected data fields. Here's a declaration of the class German address. And German address, inherits from address. Here's its constructor, and it must implement the toString method. This is just the declaration in a header file. And then here's the implementation for German address. And it's just placing the information in the appropriate order and adding, explicitly saying Germany since these addresses are going to appear in the United States. That concludes this slidecast.